Hello everyone. I'm really happy to have the opportunity to talk here today. My talk has the name Cat and Mouse or Chess. And the agenda looks as follows. First, I will give a short introduction on who I am. Then I'm going to give a short overview over how EDRs, so Endpoint Detection and Response systems, typically detect malicious payloads. Afterwards, I'm going to give an overview over the techniques that were published within the last years to bypass these userland hooking techniques or detection techniques. And yeah, after doing that, I'm going to show you first an idea I had for a new approach on how to bypass these userland hooking techniques. I'm going to talk a little bit about the challenges I personally faced when implementing a proof of concept for this idea. And afterwards, I'm actually going to show this proof of concept and will release a tool on GitHub for it so that everyone can take a look at it. So, first things first, who am I? Currently I'm a team leader at a pentest / red team at Artec Cybersecurity, which is a company located in Germany. So it's pretty much an red talk. Yeah, at work I really like to break into company environments and to move laterally there and to escalate privileges. So this is the thing which I typically like the most. And inspired by the community, I started over the recent years to also share all the knowledge that I gained. So I have published many tools, scripts on GitHub, for example. I have a personal blog post where I wrote about specific different topics. And I also made some YouTube videos, or initially it was Twitch streams, and the recordings are on YouTube. Yeah, but most things that I ever published were somehow related to AV evasion or to EDR evasion, just because this is the topic which I'm specifically interested in and what I always like the most. So, how do EDRs actually detect malicious payloads? So we have two, let's say, levels or main things where they act or where they have detections. This is the userland and the kernelland. And in the userland, for example, they could do like static analysis or dynamic analysis for any binary or for any process that is in the userland. This could be looking for certificates, as we heard before in other talks. It could also be a signature-based scan, or it could be a memory scan, or it could be any sandbox-based detection, for example. Then there's another thing. This is, I think, the main difference between classic antivirus vendors and EDR vendors, namely userland hooking. I'm going to explain that on a dedicated slide, because it's the main topic here. For example, they could also check the threat stack to detect malicious activities or payloads. And in the kernelland, the most important detections that are used are kernel callbacks on the one hand side, or it's ETW threat intelligence. So I'm only giving a short overview about these two techniques here in one slide, because the main focus is on userland hooking-based detections and on how to bypass them. Yeah, so what is a userland hook, or how could a userland hook look like? Oh, shit. What did I do? Okay. This is not my presenter, but I'm not going to try to make the red blinking light again. So, what are userland hooks about? Userland hooks are, in the very end, the EDRs typically inject or load their own DLL into any newly spawned process, at least in the userland. And what do they do there? In the very end, as you can see in the screenshot on the right-hand side, they place a jump instruction into the memory so that every time when the specific Windows APIs are called, that the jump goes to the EDR DLL, and that the EDR DLL can then do input argument analysis. So they can, in the very end, check what is this API going to do? And these checks are done on runtime. So if the payload is already running, or if the executable is already running, then EDRs can, with this technique, get an overview about what is happening on runtime. I'm going to give one more example here, because I think it's not that easy to understand if you never faced this kind of detection, or if you're not working on that level. It's not that easy to understand in the first moment. So let's imagine we have a malware that wants to inject a malicious payload into a remote process. This malware could do it by first calling open process, the Windows API, to get a handle to the process. Then it could call virtualalloc_x to allocate memory in this remote process. Afterwards, it could write actually the malware into the remote process with write process memory. And then it could call create remote thread to start the malware that was injected into the remote process. And create remote thread calls the NTDLL function ntCreateThreadX in the very end before the execution is going into the kernel land. So this is the very last point where an EDR could do analysis in the userland. And an example definition for ntCreateThreadX looks as follows. And as you can see, there is a start address as an input parameter for ntCreateThreadX. And an EDR could, for example, check what is happening at this specific start address. So if you imagine there is a malware which is encrypted, it's decrypting itself on runtime, it's then injecting itself into a different process and calling ntCreateThreadX. Then there is a jump to the EDR DLL. The EDR DLL can check what is happening at the start address. It could then, for example, do a memory scan for the location for this specific start address. And if it then finds, because at this moment the malware is actually already decrypted. So at this moment it could find any known malicious payload, such as a Cobalt Strike beacon, Sliver beacon, Covenant shellcode, or whatever else. So this is how it's working. And if it finds something malicious, then it can, for example, kill the process on runtime, because it verified actually that this is malicious. Kernel callbacks. You can imagine kernel callbacks are a little bit like hooks, but from the kernel end. So the EDRs can, with their own driver, also on specific events, do a live analysis of what is happening here. But kernel callbacks are by far not used as much as userland hooks. This is also the reason, so I personally think userland-based detections are still mainly more used than kernel callbacks, for example. Event tracing for Windows threat intelligence is somehow different, because this is an event-based subscription. So any EDR or AV vendor can more or less subscribe for these events. And these events can also indicate like memory allocation, there was something written into a remote process, there was a thread created, or something else. And they can then interact after this specific event has been captured. So this is not live compared to kernel callbacks, but it is, analysis is done afterwards. And then they could check, for example, afterwards the stack trace to see is there anything malicious, is there unbacked memory, or do memory scans, or whatever else. So what was actually published in the recent years to bypass userland hook-based detections? On the one hand side, there is unhooking. I'm giving a short explanation about how that works. Then there is the usage of direct syscalls, which I'm also going to explain very shortly, because the focus here is on a new technique. So I'm only giving a rough overview, but you can find material on GitHub and everywhere about all these topics and look them up. I'm going to give a short overview about how hardware breakpoints can be used to detect, how hardware breakpoints can be used to evade userland-based hooking detections. And I'm also giving an example and explain how DLL entry point patching works. So first things first, unhooking. As we saw in the screenshot, the EDR typically places a jump instruction into specific Windows APIs to jump to itself's DLL and to make an analysis there. This hook is typically in the text section of the DLL in memory. So if we grab a fresh NTDLL copy from disk, for example, or from any other location like known DLLs or something like that, and if we overwrite the text section of our memory from the process with that new fresh copy, then we're going to remove the hooks. And after doing that, when they are removed, the EDR will not jump to itself's DLL. It cannot do an analysis, and therefore these detections are bypassed. The usage of direct syscalls is another technique. In the very end, this concept is that instead of using NTDLL like an application would normally do, we are going to embed the specific NTDL functions completely in our own code. And this can be done, for example, like in the image on the right-hand side. This is assembly code, how a syscall would typically look like. Yeah, and these functions could be either retrieved, or the syscall numbers could be retrieved from memory. This would be proof of concepts like health gate, recycled gate, and all the other gate techniques. Then NTDLL functions could be retrieved from disk, so you could grab again a fresh copy from disk and directly push that into your own process memory and call the functions from there. An example would be deinvoke, which is a C# example on GitHub. And there is an option to partially or fully embed the direct syscalls into your own process. This would be proof of concepts like syswhispers version 1, 2, or and 3. So this would be an alternative. Again, in this case, if we have the syscall embedded in our own process, there is no jump instruction. When there's no jump, the EDR will not do an analysis, and therefore we can bypass these detections. Hardware breakpoints. This one was also, for me, again, not that easy to understand in the very first moment. It took some time to read through all the papers and through the code. But I think in the meanwhile, I got it. And in the very end, it's about that we're going to set hardware breakpoints to specific syscall start addresses. So if we want to, for example, call NT or ZV protect virtual memory, then we're going to set a hardware breakpoint to this address. And when this hardware breakpoint is hit, because we want to actually execute this API, then we are going to hide, or the code which is behind our hardware breakpoint will hide all the input parameters for NT protect virtual memory from the stack. So they will be removed and will be put to another location, and then the execution will continue with single steps, and we're doing that till the moment when we actually hit the syscall instruction itself. Because when we are at the syscall instruction, then the jump to the EDR DLL was already done. The EDR was not able to find any malicious code because all input parameters were hidden. They were not on the stack. And before actually executing the syscall, we are restoring the parameters from where we backed them up. And then we continue execution so that the NTDLL function is properly working. And one example, which is already on GitHub, and I think which was the first one doing that, is tempering syscalls version 2. So if you want to check that out, you can also go on this page and take a look at it. Another technique which was published is DLL entry point patching. The corresponding proof of concept is the tool SharpBlock from CCOP. And there are also some blog posts about this technique, which is linked here. And the idea for this technique is to create a new process, so a child process, and to debug it with the debug only this process flag. And if we set this flag for a new process, then our own namely the parent process, can act as a debugger for the child process. So we can receive specific events related to our child process. And one event would be the load DLL debug event. And if this occurs, the execution, for example, then stops. And we can do some stuff before actually continuing execution. So we can see that the EDR DLL has loaded for our child process, and directly after it was loaded, we can, from the parent process, patch the entry point in the newly spawned process so that it looks like on the screenshot on the left bottom side. So basically we're patching it with a single byte, namely 0xC3, and this leads to when DLL main is called to like return true, and it will do nothing but returning and then exit. And this technique in the very end leads to the fact that the EDR DLL is loaded, and instantly after it's loaded, it will exit and will be removed from the process, and it will never create the hooks, and there will never be an analysis done. Yeah, and then this is, at least from my point of view and from what I know, are the existing approaches on how to bypass userland-based detections. And now I'm going to show you what my initial idea for a new approach. I was actually reading the following blog post, which is linked here from Alejandro Pina. And I don't know if the name's pronounced correctly, but yeah. Yeah, this proof of concept was initially used to bypass AMSI for a new process by preventing AMSI DLL from loading into that process. And this is done by, in the very end, hooking a DLL by hooking an API function from the DLL loading process, namely, for example, NT create section. And if we hook ourselves this function, then we can basically check the input parameters ourselves as attacker and can find out if specific DLLs are going to be loaded. And if these DLLs are going to be loaded, then we return the NT status fail, for example, so that the new section will not get created for the DLL. And if the section is not created, then the target DLL cannot get mapped into memory, and it will never be loaded at all. So this is the initial idea of this proof of concept. And I had the idea, why not trying to block EDR DLLs from loading into a new process instead of AMSI DLL? One thing which is important to mention for this technique is the target DLL has to be not loaded yet into the remote process, because if it's already loaded, we can not intercept the DLL loading process. So this is a pre-requirement for it to work. And the main problem we have with EDRs is that the EDRs basically act like the white player in a chess game, namely by doing the very first moves by placing the hook, and their DLL is typically loaded directly from kernel. So they receive a kernel callback that a process was created, and they initially load their own EDR DLL directly after ntdll.dll. And so in the very end, we can say every process which is already started has the EDR DLL loaded, and every process has the hooks already. So this is a problem, because the pre-requirement is the DLL is not loaded yet. But there is some things that we could use. For example, or one example is, which I'm mainly relying on, is that if we create a suspended process, then only NTDLL will be loaded in that suspended process. So there will be no EDR DLL at all. So if we specify this specific flag, create suspended, then our newly created process will only have NTDLL loaded and nothing else. And yeah, the resulting idea, I hope it's big enough here, was then to, as malware, create a new suspended process. Afterwards, we're going to allocate memory in that remote newly created process and inject custom self-written shellcode into that remote process. And then we're going to remotely hook nt create section and place, so the hook is a jump instruction, and this jump instruction is placed to our shellcode entry point. And if we then resume the process, then other DLLs are tried to be loaded, for example, EDR DLLs, but we are already in control of the DLL loading process because our shellcode is already there, the jump instruction is already there, and for this reason we can control any newly loaded DLL, and we can also prevent them from being loaded. So this is the idea. Yeah, I had this idea like more than a half year ago and didn't start implementing it. And when I did, I had several challenges or problems, let's say it like this. First one was writing position-independent code, because we need custom shellcode. I never did that before, actually. One requirement to write position-independent code is everything that we're doing has to be placed into the text section of the executable. Otherwise, it's not dynamic, and otherwise, it will not act like shellcode, because shellcode is doing everything on runtime dynamically. We cannot use any global variables, for example, because global variables are not stored in the text section. We have, for example, to resolve all APIs on runtime, because if we do not do it like this, then our shellcode actually is not working. And then one more thing is we have to replace the main CRT startup routine with our entry point, and to more or less jump above all the code that is typically called when an executable is started. Yeah, there were more problems, at least for me, when writing position-independent code, especially for this proof of concept, because when our shellcode is called, then only NTDLL is loaded. And we cannot load other DLLs because the process is not even initialized yet. It's not fully initialized. So we have to write the complete shellcode with NTDLL DLL functions only. We cannot use anything else because nothing else is loaded. This is a pre-requirement. And then many functions which someone would maybe typically use when programming something, such as char compare, string length, memcopy, and so on, are not really usable because, yeah, let's just stay with it. They are not usable. So in my case, I was, for every of these functions, writing them manually in the proof of concept, so that, yeah, I have more or less my own implementation for these functions. I also had the big problem of debugging this proof of concept. And for that reason, I also implemented a little logger function into the proof of concept to log everything into a file. And doing that with only NTDLL functions was, at least for me, a big challenge when doing the proof of concept. Yeah, then there's one more problem or challenge, namely when the process is resumed, then NT-create section is already overwritten because we have the jump instruction to our shellcode there. But the function still needs to be called because if we don't want to block any DLL, but only ER DLLs, and to call the original function, we have to somehow restore the NT-create section value on runtime. And the solution I found for this proof of concept was the host process, namely the process which spawns the child process, already knows about the original value, and it can, in the shellcode, replace an egg. So we're basically building an egg hunter with bytes that we know, and the host process can then replace these egg bytes with the original value of NT-create section, so that this function can be restored on runtime. Yeah, then there's one more thing which I faced, namely if you take a look at any position-independent code examples which are published on GitHub, then they will probably have this kind of assembler code here at some point, and this is for aligning the stack, because if we don't properly align the stack with shellcode, then we may have the situation that it will not run correctly. But this is a problem for us, because this code modifies the stack And if the stack is modified, then the input parameters for anti-create section are also modified, which leads to a crash. So instead of using this code, which all other proof of concepts use with position independent code, we're directly jumping to our specific entry point function. We are not aligning the stack at all, and we also don't need to do this because the function which calls anti-create section is already doing that for us. Yeah, these were the problems which I faced and which were all solved. So in the very end, I can go and give you a short overview about the proof of concept and how it works. The proof of concept is written to, because it's a proof of concept, to not block EDR DLLs directly, but instead I wrote it to, check if this is working. This is my handle on GitHub, if you didn't know it. Okay. So instead, I'm going to, with the proof of concept, block AMSI DLL from loading into a newly spawned PowerShell process. And we can see if that works. So first, we're creating a new process, and we're getting the address for anti-create section. And then we are allocating memory for our shellcode in the newly spawned process. Afterwards, we're going to write the jump into the anti-create section address to place our hook. And afterwards, we are going to call write process memory to write our shellcode into the remote process. Before doing that, we are modifying the egg, so the original value of anti-create section. And then we're going to resume the process. And as you can see here, the process is resumed. And if we try to execute AMSI scan buffer, which should typically be detected by Defender as malicious, because there is a signature for it, we see that in this case, it was not recognized as a command. And if I start the PowerShell the default way, and enter the same command, we can see this script contains malicious content and has been blocked by your antivirus software. So normally, this is blocked. In our case, for the newly spawned process, this is not blocked. And we can verify for our newly created process that NTDLL is actually really not loaded by taking a look at the loaded modules. Then we can check, or we can sort by name. And usually AMSI should be somewhere here with the A, but AMSI is not there. So AMSI was tried to be loaded, but it couldn't. And if I ask you if did you ever see a PowerShell process which had AMSI not loaded, I'm assuming that no one of you did, because typically this will not happen, because it will directly be loaded on process creation. Maybe the AV is disabled, but AMSI DLL will still be there. And this is actually in PowerShell which has no AMSI DLL loaded at all, so AMSI DLL was prevented from being loaded into the newly created process. And this proof of concept indeed worked. So let's check. I think I'm really good in the time. I may have been a little bit too fast with all the other topics, but then we have more time for question and answer. Okay, so I tested this proof of concept against multiple EDR vendors, and not from any single vendor I received either an alert or the DLL blocking was prevented. And so I said there was mainly a successful block of target DLLs, because some DLLs are not loaded the normal way, like for example in this screenshot, SciInject DLL is not loaded the normal way, but it's instead injected by the EDR. And if the EDR is injecting the DLL itself, then we cannot prevent it from loading. Not with this technique, at least. Yeah. Also, as an information for those who may not know it, this proof of concept cannot be used against Microsoft Defender for Endpoint, because Microsoft Defender for Endpoint is not using any userland hooks compared to all other EDR vendors, which mainly do that. And if there is no DLL loaded, and if there are no hooks, we also cannot prevent a DLL from being loaded. So this is not working against MDE. One more thing to mention, because there are, let's say, some limitations. You might face a situation where you want to prevent a DLL from being loaded. That I faced one for one specific EDR vendor and one specific DLL. The process crashed. And I think this was due to the EDR vendor never expecting that its own DLL will not be loaded, because typically this should not happen. It's loaded from kernel and there should not be any problem. But it was blocked, it was not loaded at all, and the EDR vendor still somehow tried to interact with this process, and this led to a crash in this specific situation. So you may have to adjust this proof of concept for those DLLs to do something different, or to instead block the entry point like sharp block does, for example. Yeah. Is that implementation OPSEC safe? I think this is a question which is important for many of the red people here, especially. So injection and hooking in general have well-documented IOCs, indicators of compromise, and they are not hard to detect. So we have, for example, privately committed memory. We have a modified NTDLL version with a jump, and this should typically not happen, and this is a big IOC. And especially if you have any blue teams or hunters in your company, then they should easily be able to find those IOCs, because the initial proof of concept is not resolving these issues. It's just a proof of concept. So it could easily be found out that this technique was used. However, in this moment, or when I was testing, no one prevented this technique or alerted on it, because no one was looking for it, because it was not published anywhere. And if you don't know what to look for, you're not going to do it, and therefore, I guess, it was not blocked, although it could easily be identified. So I personally expect detections to come up after releasing the proof of concept, because, for example, an EDR vendor could, if they receive the process creation kernel callback, they could take a look at NTDLL and at tcreate section, and if it was modified, they could instantly block the process, because in the usual process started, there should not be any modifications in NTDLL. So this would be one way to check or prevent this from the vendor point of view. Yeah, there are potential OPSEC improvements for the proof of concept. Namely, you could use userland hook evasion for the host process. My proof of concept is using plain Windows 32 APIs like open process, allocate memory, write process memory, and so on. I'm not using syscalls. You could adjust the proof of concept to use syscalls instead, or to unhook, or whatever else. The shellcode currently needs RWX permissions to work, because it's doing some self-modifications, but it's not that hard to actually remove these specific parts or rewrite them in the shellcode, so that you could also use RX permissions instead, which is a little bit more OPSEC safe. The hook itself is also using RWX permissions in the moment. I faced the situation that sometimes the process crashed on specific OS versions when changing the RWX permissions to RX. So I made the proof of concept more stable, but with less OPSEC. Yeah, someone would need to investigate why these crashes occur. But in the moment, it's pretty obvious that this function is hooked, because it also has different memory permissions. The hook is also currently using the plain DLL names to block them instead of like RP hashing. So you could also replace that with RP hashing to make it more OPSEC safe. Or you could, for example, use hardware breakpoints instead of hooking for the newly created process. Then you would not have any IOCs for injection, you would still have the injection IOC, but you would not have the userland hook IOC. So you would get rid of the userland hook IOC by using hardware breakpoints instead. Yeah, this was the proof of concept. I named it Rui Lopez because I said that the EDRs act like the white player in a chess game. And Rui Lopez is a technique in the chess where, from the white player's perspective, and our proof of concept removes like the white player position for the EDR, but we are instead getting the white player, so we can do the very first moves and we can prevent the EDR from loading. So I named it like that. And the proof of concept will be published on this URL. It's not online yet, but I will do it like 5 to 10 minutes after the talk. Alternative usage IDs, you could block WLDP DLL to bypass device guard or trust checks. You could block custom AMSI provider DLLs to bypass AMSI. I also did that already. You could modify the proof of concept shellcode to afterwards decrypt and execute shellcode, fretless inject style. Yeah, or there may be additional ideas, whichever you come up with. I also have to give credits to several people who helped me building this proof of concept. On the one hand side, Cherry Coburn, because he helped me all over the way and answered questions, and also made a short telephone call with me in which I introduced him the technique, and he gave some hints. Sven Rath from my own team, who initially inspired me to build the proof of concept instead of just having the idea in my head. Alejandro Pinner, because he gave me this idea with his blog posts. Charles Hamilton and Chetan Nayak, because they both helped me when I faced problems with writing position-independent shellcode. And yes, also GitHub Copilot and ChatGPT, because I was always using them all over the way for different things.